deoxygenated blood usually has 3 oxygens bound to the hemoglobin, okay? So 3 of those heme groups will be bound and 1 will be empty, even in deoxygenated blood, which is in systemic veins. In other words, hemoglobin is 75% saturated, even in its deoxygenated state, even in deoxygenated blood. Okay, hope that was clear. All right, so we're looking at the hemoglobin oxygen dissociation curve. Which is basically how oxygen interacts with hemoglobin in terms of the binding of those 4 oxygens. So we could think about 100% saturation being 4 oxygens bound. We could think about 75% saturation being 3 oxygens bound to hemoglobin, 50% saturation being 2, and then 25% saturation being only 1 oxygen bound. All right, so this is basically the percent hemoglobin oxygen saturation. Okay, so really important that you make the connection that saturation only means how many of the 4 oxygens are bound onto those heme groups. How many of those heme groups have oxygen bound? On the X, we're looking at the partial pressure of oxygen in millimeters of mercury. And we want to think about our sigmoidal curve here. So we basically go from making it really hard. Let's use another curve here. So it's really hard to bind that first oxygen, right? Indicating this more linear part of the curve. But when we get to 25% saturation, the curve becomes more steep. So we go right up as we bind that second and third oxygen, and then the graph levels off once again. Okay, this is called a sigmoidal curve. In other words, an S-shaped curve, indicating that it's harder to bind that first oxygen, but that when that first oxygen is bound, it then becomes easier to bind the second and third and fourth oxygen on. Okay, so here we're at 25% saturation. And then we want to think about 40 millimeters of mercury being reflective of what's happening when we're 75% saturated. So at 75% saturated, which is in our deoxygenated blood, in our systemic veins, this is where the partial pressure of oxygen is at 40 millimeters of mercury. Okay. And so this really ties into what someone just asked, which is brain fart here. In our deoxygenated blood, is hemoglobin fully saturated or partially saturated? And it's basically partially saturated. When the partial pressure of oxygen is the lowest, we still have 3 oxygens bound onto hemoglobin. Okay, so let's make a note here. This is in our systemic veins. When we think about our systemic arteries, this is where we have full oxygen saturation. So this is out in our systemic arteries, when all 4 of those heme groups have an oxygen bound. Okay, and so just to describe this curve here, this is called a sigmoidal curve. Let's use a darker color here. This is called a sigmoidal curve, and this represents the cooperative binding of oxygen to hemoglobin, right? This is called cooperative binding. And so cooperative binding means that when that first oxygen comes on, the others bind with much more ease. And this explains why hemoglobin is never fully empty. It's never fully unsaturated, because it's just easier to bind those other oxygens on when we already have oxygen bound onto hemoglobin. Okay, I hope that makes sense there. We can then think about the shifting of this curve. So we can think about states that shift the curve right and states that shift the curve to the left, okay? Shifting the curve to the right makes it harder to load oxygen onto hemoglobin. So let's talk about the right first, and then we'll speak about the left shift. So essentially the right shift is seen when we have a lower affinity of oxygen for hemoglobin. In other words, oxygen and hemoglobin are not as attracted to each other as they should be, okay? They have a disattraction or disaffiliation where they don't want to bind as easily or as readily as they typically would, as this central curve would indicate. So they have a lower affinity, right? There's a lower affinity of hemoglobin for oxygen. In other words, it is harder to load oxygen. Another way to say that, it is easier to unload oxygen. Okay, and we see this in states such as increased body temperature, okay, increased altitude, and anything that increases metabolic activity. So increased metabolic activity is going to cause a right shift in the hemoglobin oxygen dissociation curve. This means that it's going to require a higher partial pressure in order to saturate hemoglobin, right? It's going to be harder for oxygen to bind onto that hemoglobin and easier for it to unload into those tissues, right? And we can think about one of the main examples of increased metabolic activity, which is exercise. Okay, let's see, we've got a question here. Okay, so I'll respond to this. It's kind of off topic. I'll respond to this in an email after class. All right, so basically we're shifting the curve to the right. And so these are things that would make sense to shift the curve to the right. Think about the fight or flight response, think about exercise, think about high altitudes, increased body temperature. These are states when the tissues need more oxygen. They need it more readily. And so it needs to be more easily offloaded from hemoglobin. And so it is ideal to have less of an attraction, less of an affiliation between hemoglobin and oxygen, okay? We want that oxygen to kind of just jump right off of the hemoglobin and move out into the tissues during things like exercise, at higher altitudes where we have lower partial pressures already. And so that is going to influence the ability of oxygen to move into the tissues. And so having the curve shift to the right is going to facilitate oxygen moving out into those tissues and not being as attracted to hemoglobin, which is ideal in these types of scenarios. And so the main message here is that it's going to take a higher partial pressure to saturate hemoglobin. Oops. Okay. So because it's harder for these two things to stay stuck together, it's going to require a higher partial pressure to fully saturate hemoglobin. Let's quickly look at the left shift and talk about the left shift here. So the left shift is going to be the opposite types of scenarios. In other words, it's going to be easier to load oxygen, but it's going to be harder to unload oxygen, right? We're going to see a higher affinity, a higher attraction or higher affiliation between hemoglobin and oxygen. So a higher affinity of hemoglobin for oxygen. In other words, it's going to be harder to unload that oxygen. easier to load oxygen. And these will be the opposite types of factors. So decreased temperature, all right, decreased altitude, or anything that decreases metabolic activity. Okay. And so basically, again, thinking about the scenario in the opposite direction. If I have well oxygenated tissues, if I have decreased metabolic activity, if I'm at lower altitudes with higher partial pressures, I don't need oxygen to be as easily moved or readily offloaded into my tissues. And so oxygen and hemoglobin have a tighter attraction, a tighter affiliation, and they don't separate from each other as easily, whereas it is harder to unload it. So it's going to take more, it's going to take a lower partial pressure in order to fully saturate hemoglobin in this instance. Okay, so let's put that note here, and we'll start off next time we meet by just kind of going over this. So a lower partial pressure is required to fully saturate hemoglobin. Okay.